Now we consider a problem where we want to find the path of a particle. In particular, this particle is in a field, therefore it is subject to forces, and we want to use the variational principle, which is called the Maupertuis principle that we will see now, to derive the path of a particle. The particle is moving with a constant energy, so we'll assume that the energy E of the particle is constant. Let's start with the expression for the energy. So we know that the kinetic energy plus the potential energy gives us the total energy E. So T is the kinetic energy and V, as usual, is the potential energy. Now we consider a particle, so the kinetic energy can be written like this. It is 1/2 the mass of the particle times, I will rewrite it like this, dl over dt squared plus the potential energy, where dl, if you think about it now, here I will draw a very general sketch where this line here, this curve, represents the path of the particle. So if I just split into several parts, these small elements here are just dl. And if I consider, for example, an origin here, this position vector, which I can call r, describe the position of each point on the trajectory, on the curve. And therefore the differential dr is the vector that's tangent to the curve, and its magnitude is equal to dl. So dl squared can also be thought of as the dot product between dr with itself, dr dot dr. Now I can use this equation above here to derive the expression for dl squared. So dl squared, if I solve that equation, can be written like this. It is 2e minus v divided by m dt squared. Therefore, from here we get that dl is equal to square root of 2e minus v divided by m dt. Now let's write down the expression for the Hamiltonian of a system that's constituted by one particle. The Hamiltonian h is equal to E, which is the energy, and it is a constant. And I can rewrite it as the momentum P dot product with r dot, the velocity, so I can simply write the velocity as r dot, which is dr, this dr here over dt, minus the Lagrangian. So the Lagrangian can also be written as P dot r dot minus the Hamiltonian h, or if you want, minus the energy E. Therefore, the action can be written as an integral of the Lagrangian, but the Lagrangian is equal to this, so it's an integral of P dot product r dot times dt, but that's just dr, minus the integral of a constant, which is the energy. So it's the energy times Tf minus T0. Tf and T0 are the two endpoints of our path, and the variation will not affect this part, because when doing a variation I only vary the trajectory between the two endpoints, but I do not vary the two endpoints, they remain fixed. Therefore, I can write the following. The variation of the action is just equal to the variation of the first integral, P dot dr. And I know that I can rewrite the momentum as the mass of the particle times dr over dt, which is the velocity, or r dot if you want. This is dot product with dr. And I can also divide this by dt and multiply by dt if I want. But dr dot dr is dl squared, so I can rewrite this as delta integral m dl squared over dt squared dt. And this is equal to variation of integral, I have the mass, and then I have dl squared over dt squared, which I can also rewrite from here, because dl squared over dt squared is just equal to 2e minus v over m. So here I have to multiply this by 2 e minus v divided by m, and then I have dt, which I can also rewrite using this equation here, because I want to rewrite, instead of dt, I want dl. I want to express the integral in terms of dl, which is the trajectory after all. I want the trajectory. So dt can also be rewritten as square root of m divided by 2e minus v times dl. And that's what I'm going to put here. So I have square root of m divided by 2e minus v dl. And I can rewrite this as variation of integral square root 2m e minus v dl. And I want the variation of the action to be equal to 0. Now when I reformulate the action principle in terms of dl, this is called Maupertuis principle, and therefore I can get rid of this factor of square root of 2m, because I just want to find the path of the particle. So I can just simply take the variation of this integral here, integral square root of e minus v dl, and I have to set this equal to 0. Now I want to calculate this variation, and it is very easy if, for example, the potential energy is equal to 0. That means that the particle is free to move, doesn't have any constraint, no forces act on the particle. So it means that if v is equal to 0, then we have to minimize the length of the path, and the length of the path is minimized when, of course, it is a straight line. So in this case we get that the particle moves in a straight line, which is something that we know from classical physics. But if there are some forces acting on the particle, we have to rewrite this equation here. I have to vary the path by changing r. So the variation of that can be written like this. Integral, I have to take the derivative of the square root with respect to r, and of course e is a constant, but what depends on r is v. So I have minus dv over dr, the gradient of v with respect to r, dot product variation of r times the derivative of the square root, which is 1 over 2 square root of e minus v dl. And I also have to vary this dl here. This dl changes if I change dr. So I have plus square root of e minus v variation of dl. And we have to find this variation here. The variation of dl, which is also equal to the differential of the variation of L, if you want, but I'm going to use this one now, is equal to the variation of the square root of dr dot dr, because dl, of course, is equal to the square root of the dot product between dr and dr. And this is equal to 1 over 2 the same square root, which is dl, and then I have to take the variation of what's inside the square root. So I have differential of the variation of r dot product dr plus dr dot product differential of the variation of r, and this will give us dr dot product d variation of r over dl. Therefore I can rewrite this integral here like this: integral minus dv over dr dot product dr dl over 2 square root of e minus v. The first integral remains the same, and then I have plus square root of e minus v, and here I have dr over dl dot product d variation of r. And now what I'm going to do is I'm going to integrate by parts this second part of the integral. So the first integral will remain the same, and I have integral minus dv over dr dot product dr over 2 square root of e minus v dl, and then I have minus. I get a minus from here because I'm integrating by parts. So when I integrate by parts, I have this term which multiplies this one, and I have to evaluate them at the boundary. But when I evaluate these terms at the boundary, the variation of r is going to be equal to 0 because I keep the endpoints fixed. So I only have minus integral of. This differential now will act on this. So I have differential of square root of e minus v dr over dl dot product variation of r. And this must be set equal to 0. But now, since the variations are all independent and arbitrary, the term that multiplies the differential delta r can be set equal to 0. So we get that minus dv over dr is equal to 2 square root of e minus v d over dl of square root of e minus v dr over dl. And now we can rewrite the gradient of the potential energy with a minus sign as a force. This is the force acting on the particle by definition. And then here on the right hand side I can take this derivative. So this is equal to 2 square root of e minus v, and then I have 1 over 2 square root of e minus v, and then I have minus derivative of the potential energy with respect to r dot product dr over dl, and then I have dr over dl here plus square root of e minus v d squared r over dl squared. And now minus the potential energy over dr here is just the force acting on the particle, and dr over dl is a vector that's tangential to the path of the particle. Dr has the same magnitude as dl, so this is a unit vector and it is directed along the tangent of the curve. So I can just call it tau hat, which is a unit vector tangential to the curve, and this is also tau hat. So here we get, if we take this term over to the left hand side, we get f minus f dot tau equal to 2e minus v d squared r over dl squared, and this term here is just the component of the force along the tangential direction. So if I remove the tangential part from the force, here we only get the component of the force along the normal to the curve, and it is a vector, of course, so it is the direction normal to the path, whereas E minus V is the kinetic energy of the particle. So twice that I can rewrite as the mass of the particle times the velocity of the particle squared, and I'm going to call the velocity W squared in this case. Then I have this derivative here, which I can rewrite as d over dl of dr over dl, which is the tangential vector. And dl can also be expressed as the radius of curvature of the path, which multiplies an angle d theta, which is measured like this. So if I have a very small portion of the curve which has a length dl, here, somewhere here, I have the center of the so-called osculating circle, which is the circle that contains dl and here has a radius that's equal to the radius of curvature. So this is supposed to be a circle, and here we have the radius of the circle, which is the radius of curvature, and here I have d theta. R d theta is going to give me dl. And then, of course, here I can rewrite this expression as 1 over r d tau d theta. And if I consider a very small variation of tau with respect to the angle theta, I'm going to get a vector that's going to be perpendicular to the tangent, and therefore the direction will be that of the normal. And this will be a unit vector, which I can call n hat. This is very easy to prove because, for example, I can choose a reference frame where tau can be written in a very general form like cosine theta, sine theta, if I'm considering the plane where the osculating circle is defined. So I have just two components, cosine theta and sine theta. This is a very general orientation for the vector tau. And if I take the derivative of that, I get a vector minus sine theta cosine theta, which is still a unit vector, as you can see. So this is n. And therefore, finally, what we can write down is this. The force that's normal to the path is equal to the mass of the particle, velocity squared of the particle divided by r, the radius of curvature, in the direction of n, the unit normal. This expression should not surprise us because it is in agreement with the familiar expression for the normal acceleration while moving in a curved path.